Today's session is AVL Trees. So, you know about binary search tree. Last class we saw about binary search tree. Binary search tree, the main condition is actually uh, your nodes which are lesser than your root node will be placed on the left side, and nodes which are greater than the nodes will be placed on the right side. So this is what your normal binary search tree. So whatever nodes come that lesser to it, it will be placed. So even though when you in the subtree, even if you are taking a node smaller, if you are taking a node, parent node, uh, to the left it should have the child lesser to it, and to the right it will have the child greater to it. So this is the normal procedure of binary search tree. And coming to AVL trees, AVL tree is one of the binary search tree only, one of the concept which is included, which includes binary search tree conditions named after. So that name is called as Adelson Welsky Landis. That is what A, V, and L. Okay, Adelson, Welsky, and Landis. That's the term is called as AVL, and it is called as height balancing binary search tree. So it is also a binary search tree only, provided with height. So this is the main thing which we are going to calculate in your AVL. So there is a special factor called balance factor. That means the height of the left tree and the right tree, it will check it out, and this should be calculated based on the balance factor. You have to find out whether you can balance the particular tree. If it is not balanced, you have to balance it. That is the technique we are going to follow here. So here, for example, you see here B is my node, and to the left I am having one node. So your balance factor is, height of the left subtree minus height of the right subtree. That is the meaning. So, so are you able to see the screen?
Yes, ma'am.
Yes, ma'am.
Ah, yes, okay. So balance factor will be uh, balance factor F. So height of the left subtree minus height of the right subtree. So height of this is, now from this node the height is only 1, right? So 1 minus, to this also it is 1. So 1 minus 1, so it is 0. When you take this node, there is no, this is a leaf node, there are no nodes below, so it is 0. And when you take C node also it is. So for each node you have to calculate the height. Now come to this node. So this is balanced, because balanced in the sense your balance factor should be 0, minus 1, or plus 1. That's all. Apart from that, if you have any number, the tree is said to be unbalanced. So AVL, that particular person has designed the AVL tree, an inventor has designed in such a way. So uh, so height is C now, that is C node. And now see here, when you take this node, what is the height of C? You know to calculate the height from the root to the leaf, that is the height. So 1, or from the node to the leaf. So 1, 2. So my left side height of the tree is 2, minus right side, no, nothing is there, so it is 0. So 2 minus 0 is 2. Similarly, when you take B, my height of B is only 1. So 1 minus, there is no right tree, so 0. 1 minus 0, 1 only. And for leaf node, always 0. So since you have a balance factor 2 here, it is considered not balanced. Okay, if it is 1 means it is balanced, I can tell. Your balance factor can be only 0, minus 1, and plus 1. Similarly, when you take for this tree also the same thing. Here there is no left side, this should be minus 2. Height of left subtree minus height of right subtree, this will be minus 2. Minus 2, and this will be minus 1. Okay. So this A will be, there is no left subtree, so 0, minus height of the right subtree is 1, 2. So my height is minus 2. Similarly, for B, there is no left subtree, so 0, minus Right subtree only 1, so minus 1. Here it is 0. So this is what your balance factor. So see in this whole tree, when you take also, you can see that there is a minus 2, which is not considered to be balanced. So if the tree is unbalanced, you have to balance the particular tree. That is the method
Ma'am,
to be
Ma'am,
followed. Yes.
on the
if
first one, how
only
do you have
A and
minus
T
one
are
plus one?
What ma?
Ma'am, how do you have minus one and plus one in the first?
No, no, no.
Zero
This is
minus.
a standard for
Okay.
balancing factor. To find out the balance,
Okay.
no, this is not applicable to this. This is separate. For
Okay.
having a standard, how to find if the tree is balanced or unbalanced is find the balance factor, and if it includes these three, it is okay, balanced. If it is not from these three, then it is unbalanced. Okay, that is what general condition. So now,
ma'am,
yes.
in the say the rightmost one, the A, B, C is there. If
Hmm.
only two are there, A and B, then it will be balanced, right?
Yes, A, B is there means, yeah, it will be balanced. This will be minus 1. This will be 0. So it is a balanced tree. Understood? If A, B are only there, it is a balanced tree.
Ma'am, in the third one, why is it
Hmm.
-2 instead of 2?
See, height of formula is height of left subtree minus right subtree. So 0 minus 2, what is the answer?
Okay, ma'am.
Minus 2. So that is what. So balance factor, this is the formula which you have to keep it in mind. Height of left subtree minus height of right subtree. And it can be minus 1, 0 or 1. And minus 1 means it indicates that your right subtree is greater than the left. So you could see here. If this is greater, right side is greater only, you will be getting in minus. 0 means all are equal. Plus means your left is greater. That's all. Oh, sorry. So the same thing is repeated here. It should be a binary search tree, and I think the slide is repeated. So and the maximum possible heights, you can note this and keep. It's a formula. And why it is log and all, you will learn it in the ADA subject. But you should know for MCQ purpose, time complexity will be log n O of log n for because it is binary search tree ordered on. So it is log n only. It will be divided and only accepted. So that explanations regarding these all, you will be learning it in the fourth semester. Now balance factor. Now see this tree. Take this tree and look into it. Balance factor. Is it right or anything goes wrong? So what is the height of 25? Height of left node? What is the height? Don't count the nodes, okay? Don't count the nodes. Every time if you count the nodes, you count the level. Level. So what is the height of the 25 first? What is height of the left subtree?
Three.
Third, 3.
3 minus
Three.
1, 2, 3. Okay, 3. So 0. Understood? Similarly, here, what is this height?
Two.
2 minus only
One.
1. Okay, so this is how you have to follow. So when you look into this also, I think you could understand. What is the height of 10 left subtree?
Three.
Minus
Four.
1, 2, 3, 4 levels are there. So, okay, so 4. Height of the right subtree is 4. That is what it is, minus 1. So when I take all, when I look into each of the node, all are minus 1, 1, 0. So it is a balanced tree. Here also 0, 1, minus 1, all are balanced only. There is nothing like 2 or 3 or nothing is there. So these both are balanced trees. So this you can check it. This is for your exercise purpose. You can check whether it is balanced or unbalanced. And these are the one which I have explained. Now what are the operations? Operations you can do always: searching, insertion, deletion. Normally in all the data structure concepts we do this. So search operation. So normally when you want for a search operation, a normal procedure is you check whether the particular search element and you start from your root node, whether it is equal or not. If both are exact match, you can tell that it is found. Otherwise you will be checking This is exactly like your binary search tree, which I told you. You will check whether the searching element is less than or greater than the root node. If it is lesser, go to the left subtree and search. If it is greater, go to the right subtree and search. Still, if you are not able to find out, even after so many recursion or even after so many steps, you can tell that element not found. So when you come for insertion, here only your AVL main concept itself starts from here. Always you have to check the balance factor, and you have to check whether it is 0, 1 or -1. If the tree is balanced, no problem. You can leave it as such. If the tree is not balanced, you have to, if it is imbalanced, you have to do rotation. This is a very important concept in AVL. You have to do rotations to balance the tree. After doing rotation, if your tree is balanced, then you can stop your rotation. So AVL tree rotation is of two types, mainly two types. That is, there are four types, but comes under two rotations: single rotation and double rotation. Okay. So single rotation means uh, that is only once you will rotate. Left single rotation, that is left rotation, right rotation, left right rotation, right left rotation. So here, by the name indicates, it is left rotation. That's all. You're rotating only left. Here you are rotating only right. And double rotation, you will be rotating left, then you will rotate right. Here also you will rotate right, and then once again, see, when you rotate left, it will not be balanced. How to find single and double rotation is, first when you are inserting left, after rotating left, still the tree is not balanced, means next you will be rotating to the opposite side only. So it becomes a double rotation. It won't be like, yeah, two times continuously you won't do left rotation. If you are single rotation, left rotation you will do, called as LL. Right rotation you will do, called as RR. Left, once you have rotated left but still your tree is not balanced, means you will be doing right. That is called as LR rotation and RL rotation, right and left. So if you are doing two times continuously, if you are rotating, it is called as double, otherwise single rotation. Easier only. If you understand, it is very easy. So left rotation means, that's what I told as LL. Normally your procedure, what you have to follow is, if you are inserting in the right side, if any node is inserted in the right side, you rotate it to, you take the left rotation. That is the trick which will be followed normally. Otherwise, through algorithmic wise, if you see also, see, look into, if a tree become unbalanced when a node is inserted into the right subtree of a right, that is right side, then we perform single left rotation. See, for example, A is there, B is there, C is there. Now you can know that it is unbalanced. You know how to find the balance factor of each node. So node is unbalanced now. So what you have to do? This side seems to be the, that is, it is right side, it is skewing down. So I have to make it balance, means if I rotate the other way, left side, if I rotate the left side, my tree would become balance. Okay. So what they are doing is, they are rotating like this. So when they rotate, B and A will be rotated. So B will be taking the root node, and this node will come to the left of B. That's all. So now when you calculate, it will be showing that all are zeros. So one example I'll show you. Wait, see here. This example you can see, there is 1 and 2 already. 1 and 2 is already there, and I have calculated the balance factor also. That is -1, 0 -1. That is the meaning. This side no factor side, 0 -1. That is the meaning. So -1, and this is 0. Okay. So now I am going to insert 3. Where will I insert 3? Normal binary search tree insertion. 3 will be compared with 1. It is greater than 1. So right side only it should come. Right side, but already 2 is there. Compared to 2, 3 is greater. So choose right side, you will get 3. So I have inserted now. I have inserted the 3 now. Once after insertion, once again calculate the balance factor. What is the balance factor of 1?
-2.
minus 2. So 0 and this one, these two heights are there. So minus 2, minus 1, 0. So this is unbalanced now. So when this is unbalanced, you have inserted in the right side. So try to rotate the left side. Take the left rotation. Okay. So left rotation means this side you have to rotate. That's all. From 2 you have to start. This 1 will come the left of 2. And provided you have to, when after a rotation, two things you have to keep it in mind. One is balance factor. Calculate again the balance factor. All are zeros. So your answer is correct. Another one is check for the binary search tree condition. What is binary search tree condition?
Left side has to have smaller numbers, right side has
Smaller.
to have
Yes,
bigger
yes,
numbers.
good. Right side greater number. So when I make 2 as the root node, my left is having smaller to the 2 and right is having greater to the 2. So that is also satisfied. So my answer is correct. Okay. So this is how whenever you make rotation, after rotation, you can rotate any side. Actually, if you rotate at the correct side in a single way itself, you will finish the answer. In case if you rotate it wrongly, you will find the technique that you have rotated wrongly, and you will, when you are doing it manually, I'm telling, you will rotate it in the right way. But whatever way you find the rotation, the thing is, two things has to be checked finally. One is your balance factor, and another one is your binary search tree condition. If both are satisfied, only your rotation is right. Otherwise you have gone somewhere in the middle, you have gone wrongly. That is the meaning. So now same thing I have told about LL rotation. Now RR. RR means right rotation. So right side means till now we were rotating this side. Now we will be rotating this side. That's all, right side. So this comes. So now I'll go with the example. So example 3 and 2 are there. I am inserting 1. Where will 1 come? I'll compare with, don't suddenly go and put the node under any one of the where it is free. You should not, that is not the procedure. You should compare one by one. Compare 1 with 3. 3 compared 1 with 3. 3 is greater, 1 is lesser. The node to be inserted is lesser. So go to the left side of your what is that? Left side of your node, root node. So left side of the root node already 2 is there. So again, what 2 compared to 1 and 2, again 1 is lesser. So again a left side of 2 only. So I have added to the left. Now I have calculated the balance factor. It is height is 2. So 2 minus 0, 2, 1. So when I check the height, this is an unbalanced one. So rotation is compulsory. So I have made a right because I have inserted to the left. I will do the right rotation. Right rotation means just 2 will come in the right side of 3. Now check it. All are all are zeros, balanced, and as well as satisfying the binary search tree conditions also. Okay. So this is your LL and RR rotation. Now come to left right rotation. So this is a combination of left followed by right. Okay. The tree itself, you can see this tree, this type of trees, when I take splay tree, I will tell you what is actually this is like. Wow, if it is in the straight thing, one will be, there are three types of splay trees, zigzag, zigzag, and last one is zag zag. So when I take splay, I'll tell you, if it is like in this way, this is something, one is in one order, that is this order, and it is not in the continuous order, it goes like this, it is like zigzag. So this if the tree is like something an unbalanced one and not in the same position, or means normally when we look into itself, we can tell that it needs double rotation. See, if all are in the, here you could see all are in the same side skewing. Even in the before diagrams, if you see also, either it will be in this side or it will be in this side. So only one rotation is enough mostly. But if it is something one side skewing and the next coming to the other side, normally mostly you will go for two rotations. Mostly, I'm not telling always, most of the time. So but we can find it easily. When can we do double rotations? So when I take this, what I have to do is, I have to do one time LR no left rotation first, then that is this both I will do first left rotation, Why I'm doing, when I do left rotation here, what will happen is C will come here, then A will come. No, not A. Then because left, no. So left rotation means like this. It should go. It will be going like this. A and B. So B will be coming next, and this side I will get A. Okay. So I have made now as a single line. So I have done the left rotation. This is LR. So left is over now. Now I will do the right. So when I do the right, what I will do, B will be acting as your parent node. A will come here, and then C will come. So now my balance factor will be right. So when a tree is something like not a normal skewed, if it is only this skewed, or you could find only road. Here first you are making it to one particular order, that is left rotation is done. Then you are doing a right rotation and making it. But how to follow it, I'll tell you. Wait. So that's what diagram which I have drawn here only, it is done here. Left is done. So it is so each time when you rotate it, you have to find the balance factor. So after left also still 2 is there. So once again right is done. So this what till here only I have done in that diagram itself. Now see in this thing, insert node 2. In this example you can see insert node 2. When you are inserting node 2, what happens is it audible?
Yes, ma'am.
Yes. Okay. When you insert node 2, see here, where will node 2 come? Already 3 is there. Already 3 is there. So it will compare with 2. And what will happen? Where it will be inserted alone, you tell me. Oh, this should be actually 1. This is 1. Okay. So where will node 2 come?
Right,
Right of
right child of
Right
node
of
1.
2. Yes, so the right side of node 1. Yes, because 2 it will compare, it is lesser, it will come here. Again, it will compare with 1. When 1 and 2 is compared, actually it is 2 is greater. So it should come in the right side. So now I am going to calculate the balance balance factor. So for my node 3, it is 1, 2. So 2 minus 1. 2 minus 1, 2 minus 0.
Minus 0, ma'am.
2 minus 0. So 2. Again 0 minus 1. So minus 1, right? Okay. So now it is unbalanced. I found that 2 and these 2 is an unbalanced one. So first what I will do is I will do some left rotation. See, you can ask, ma'am, without this, shall we do left rotation of this? When you do left rotation of this, will you get the answer correctly? When you rotate 3 and 1, it will go wrong actually by procedure. What will happen is 3 will come here. What, that is, for example, if I'm rotating 1 and 3, what will happen is 1 will go here, then left, no? So 3 has to come this side to the left of this. Is it right? Is it right? When I rotate this both, I'm telling it will come.
That will happen, but it will be wrong.
Yeah, it will be wrong. That's so
Ma'am,
we
one
are.
small doubt.
Uh,
Do we change the address of the uh, do we change the address of the node when we are shifting?
No. Address will not be changed.
Okay.
Okay, so only thing we are concentrating only on the data,
Okay.
the particular where it goes and gets stored. That's all. But we are not going to change the address or anything else. Okay, so now see here. Now if I see here, this both will be rotated first. So when you rotate this both, it does not gives us a good answer. So I will rotate this first. Since it is in the right side insertion, this is in the right node. Okay, see, don't see from the root node where it is inserted. Always I told you, know, when you are inserting in the right side, you will be rotating to the left. When you are this is a technique which you have to keep in mind. When you are inserting to the right side, you have to rotate left. When you are inserting to the left side, you have to rotate right. This is the procedure followed. But don't look that insertion from the root node. See, from 3 when I looked into, This insertion 2 seems to be in the left side, right? That if you see that, then again you will be in confusion. Immediately to the previous parent node, you see. So my 2 is inserted to the right of 1. So that only you have to consider. So to the right side it is inserted. So my rotation should be in the left. When you decide the rotation, you can find out whether it is L or R. Or LL, RR, or LR, or RL. This is the 4 types, right? So when you insert it in the right side of 1, you know that you have inserted right side. So my rotation I have to do it in the left. So either this will be choosed LL, or this should be choosed. So first time I do not know whether when I rotate whether it will be balanced or not. So first time making a left rotation, that's all. A left rotation is made between 2 and 1. So directly 2 will come up, and to the left 1 is coming. Now you are calculating the balance factor. If your balance factor is right, you can leave out with the single rotation, but our balance factor is not right. So once left is right, the next rotation should not be again left, it should be the opposite of it, right. Okay, so this rotation is automatically chosen. LR is chosen, and you are done with the particular tree. Anyway, there is an example. I'll tell you with the big example. First, you know the concept alone. So, right, similarly, RL rotation, the same thing. See this is like this side, zigzag. So RL, this is the left side rotation. That is the meaning. Here, left side, the rotation is made. So I have to move, I have to rotate to the right. When I rotate right, my node will be A, then B. That is when I rotate right, B will come up, and then C will come. So it is one particular skewed. Then again I will, so I,
Keep C in the middle, right?
what ma?
And B. And
Wait, I'll show you the diagram. Rotate. Oh, okay, okay, okay. Yeah, this rotate I have done like this rotation should be from along this side. Rotate right. Okay. Now I think you could understand that arrow mark I have put it wrongly. Rotate right. So B will go up, C will come down. Is that right? Rotate right, ma. B and C will be rotated first. This part will be rotated
Yes, ma'am.
first. Okay, see here in this diagram I'll show. B and C is rotated. So B will go there, C will come down. Now again, after rotating right, again I have to rotate left. So because it is unbalanced, so I will rotate left. So first I have rotated this side to come to the right side. Now I will rotate left like this. So B will go up, A will come down. So B will go up, A will come down. Okay. So with the example, I'll tell you now. Example 1 and 3 is there. I'm insert node 2. Yeah, insert node. Which node I'm inserting? Yeah, node 2 only I'm inserting here. That's one is changed. Okay. So insert node. So when I compare 1 with 2, 2 is greater. It should come in the right side. But right side already 3 is there. 3 and 2 will be compared. 2 is lesser. So 3's left will hold the value 2. Now I will find the balance factor. Balance factor is -2. So since I have inserted in the left side of 3, I will rotate right. So I will do the rotation like this. I will rotate right. So 2 will go up and 3 will come down. 3, see, don't put 3 in the, when you rotate, please be careful. By mistake, even if you put 3 this side by mistake. For example, I'm telling, by mistake, if you put 3 this side, you can easily check it is not satisfying the binary search tree condition, because 2 is smaller than 3. 3 should be in the right side of 3. So immediately erase it and put it in the 3. When you rotate, sometimes some people make a mistake by when they do it in a hurry. Say what they will do is suddenly they'll do like this 2, then again they are rotating, right? So 2 they'll put, and directly this is left, no? So I have seen many students putting 3 over here when they wrote this is 1. So 1, 2, and directly when they rotate 2 and 3, what they will do is just the reverse they will do. 2 they will put it that side, 3 they will put it down. So this is actually right or wrong?
Wrong, ma'am.
Wrong. Why it is wrong? Because
Binary search tree
yeah,
condition.
binary search tree condition is failing here. 2 is smaller than your left side node. Always I told you, whichever node you take, compared to the parent node, this side it should be less. So immediately, even by mistake, even if you rotate wrongly, then immediately cut this side and put the 3 over here. Okay, clear? So this is right now. Now, but still there is unbalanced factor. When I calculate again, there is unbalanced factor. So what I will do, right side I have done, so I will do the left rotation. Left rotation now, where you have to do, you have to rotate 2 and 1 only. 2 and 1 only, because this both rotated. Now 2 and 1 I will rotate. So 2 and 1 if I rotate, it will come in the left side. Okay. This is what your RL. Now see this example. Insert these numbers and apply the rotations. Okay, so this partial tree is already given. Sometimes they might give, or they will be directly giving the numbers alone. If they directly give the numbers, start it from node 1. 1 will be your root node. Then what you will do, you will insert 8. 8 is greater, so you will put it in the right side. For binary search tree, you can just insert and you can finish it off. But for AVL, each step, when you insert, you have to calculate the balance factor. Understood? For binary search tree, if they give a series of numbers and ask you to do the binary search tree, fulfill the binary search tree, you can just keep on adding and you can leave. But for AVL, each time when you add, you have to calculate the balance factor immediately itself, not after inserting everything. Each time you insert and you have to calculate and rotate. So now see here,
Ma'am,
forget about this tree now. Huh?
ma'am, if there is a big binary tree and we have balance factor like not -1, 0, and 1
Hmm.
for the main head node and also for another node, then
Hmm.
which one should we rotate first, like head node or the lower node, which is not balanced?
No, wait, after this example, I think you can find it out. Wait a minute.
Okay.
This example contains a bigger tree only. You can listen. At that time, you will know it more clear. Now, see here, if this tree
Ma'am,
is not
you said that after inserting one node, we have to rotate. We have to rotate after inserting every one node. Now,
mm,
in the given binary tree, if there was, say, if 10 was not there, that means if it was unbalanced, then
mm.
would we have to first rotate it and balance it, or we have to first insert and then
No,
balance?
that's what I told you. You have to rotate it and only then balance. That is, you have to balance it and then only insert.
Okay, ma'am.
Balancing only rotation, balance it, and then that's what I'm trying to tell you now. I've started to tell. So if you're, if in case if this tree is not given, forget about this tree. Yeah? If only numbers are given, just first take the first node as the root node. If the root node is not provided over here, you have to go in order. First node, root node, then next 8. So I will insert 8 as a greater than 1. I'll insert it in the right side. Now I will calculate the balance factor. For this it is 0. For this it will be -1. So it is balanced. So next I will take 20. 20 is greater than 1. So right side greater than 8. So right side. This is I'm telling if it is a plain tree without anything. In this example, there is already a tree. Here I have to go and insert. This is my creation, initial creation without if there is any tree. So now 20 is there. Now again I will calculate the balance. Now I have inserted 20. Now again I will calculate 0, 0 minus 2. Minus 2. And this is -1. Right? This is 0. So now I could find that this is unbalanced. Directly you should not go and insert 9 now. If I insert one number, immediately I will find out whether the tree is balanced or not. Okay. Once if I find the tree is balanced, I can go move for the next insertion. So what I will do now is -2, -1. So now this is unbalanced. Now
Left
I
rotation.
will do a rotation. What rotation I will do? Because I've inserted on the right side, I will rotate in the left side. Okay, so 8 will come now. Again, this side I will get 1, and this side I will get 20. Okay, now only, now again I have to calculate the balance 5. I think all are zeros. 0, 0. Now again I will insert 9. Where will I insert 9? 8 greater, 20 lesser,
Left of 20.
left of 20. Yes, good. So 9 will come here. So when so when 9 comes here, once again I will find the balance factor. This is 0. Leaf node, I'll put 0 first itself. Now again, so for root node it will be 0 and 2. So this is minus 2, right?
-1.
-1, ma'am.
Yeah, 1 minus, okay. 1 minus 2. So this is minus 1. Okay, this is minus 1. And this is 1. So I think it is balanced. So once again, next I will apply 12 in this diagram. So I will go for 8 greater than 12 greater than 8 right side here. But compared to 20, 12 is the lesser. So this side. Now compared to 9, 12 is greater. So come this side. So 12 I will put it here, right? I'll put here. Now again I have to calculate the balance factor. So what I will do? What I will do, ma? What is the balance factor of 8? Tell me.
-2.
-2.
Minus 2. Okay, 0, 1, 1, 2, 3. Okay, 1 minus 3. Next, this one?
-2.
2.
Mm,
-2. Sorry, 2, 2.
minus
2.
Positive.
2. How it is minus 2?
Got confused, ma'am.
There is no 0 that is 2 minus 0. So 2. Okay, 2. So this is 0. Again, this is minus 1. And this is 0. So now I have to balance, right? So where I will balance, even though this is minus 2, don't go and jump over here. Just look this side. I have already told you the format of this. Just look this side. You have inserted 12 where? In the right of 9. That is right side. Right, I have inserted 12. So what I will do is, I will rotate to the, where I will rotate?
Left.
Left. So insertion is in the right side, means rotation will be in the left side. So how will I get my tree now? How will I get my tree now? This side I will get, this side I will get
12.
12, and this side I will get 9. Is my binary BST condition satisfied? Binary search tree?
Yes, ma'am.
Yes,
Yes.
ma'am.
Now I have to calculate the balance factor also. So balance factor, tell me the balance factor of this 8.
-2 only.
-2.
Minus 2, okay. 0. Again, this is 2 only. This is 1,
1.
and this is 0. But still it is not balanced, no? So already what rotation I have done?
Left.
Already left rotation. So now I have to do the,
Right.
wait a minute. Okay. So I have to do the right rotation. Now you have to see that, listen here. Now if I do a right rotation here, now I have to find whether it is balanced. What I will do is, right rotation I will do with this part, right? And this I have rotated. Now I will do with this part. So my 12 will go up and 20 will come down. Okay, so I'll put the eraser now. Yeah. So here I think 12, right?
Yes,
And
ma'am.
this side
20.
20, and this side 9. So this will be erased. Now calculate the balance factor. Um,
-1.
1, 2. So 1, so minus 1. Now for this it is 1
0.
minus 0, 0, 0, 0. Now it is right, no? Balanced. Okay. So this is how you have to do. Now it is balanced. Now I'm coming to this tree now. Now till now what I have explained is only with this. If it is a new tree, if it is a fresh tree, how what I should actually do. This is the way to do. Now if it is already some already partial tree is given, I am going to insert it one by one to find out the how to balance the particular tree. So already 7, 5, 10 is given. So where should one be inserted now? Now you have to only answer now. Then only it will be more clear.
Left child
Where
of
will one?
3.
Left
Left of
Left
3.
of?
3.
Okay.
3.
So you can see there it is in the left of 3. You have a 1, and all balance factors are calculated, and you can find that unbalanced. And so do the where you have inserted left. You have inserted in the left side. So you rotate it to the right side. So since they have rotated, see, if you can ask me, like, ma'am, we have inserted here, and if I'm rotating this side, will you get the tree correctly? If you rotate 3 and 1 for the right side, if you rotate 3 and 1 right rotation, if you do this, will you get it correctly? You will again form it into a zigzag tree, right?
Yes, ma'am.
So go to the above one stage. This is how which you have to find actually. When a bigger problem come, if you practice 2 or 3 problems, it will be easier for you. After that, you will be more clear. But if you rotate this both, what happens is automatically you will not achieve the target. So go to the above one. Above one, try to rotate 3 and 5 and rotate and see. If you rotate this both, it will not work out. Okay, rotate 3 and 5. When you rotate 3 and 5, your 3 will go up. What will happen is your when you rotate 3 and 5, what happens here actually? But here actually that is also not rotated. 3 and 5, when you rotate, what happens? You have to check it out. When if I rotate 3 and 5, what will actually happen? 7. When I give a 3 rotation to the left rotation, there will be a great confusion over here in this node. What happens is 3 will go up, and that is here it will come. 3 will go up. Let us check it. My tree can vary. Sometimes it is not the final answer. Everyone will not get the right answer. The thing is, 1 or 2 child will be in some other places, but actually it will be balancing both the conditions. If that is also the case, actually your answer is correct only. So now if I try to rotate 3 and 5, what will happen is 3 is going up, right rotation, right? So I am doing like this. So 3 going up, right side of 3 I will be getting 5, and left of 3 there is 1. Now 7, and then remaining I think as it is I'll keep it. Okay, and is that right? Is that right? Right rotation I have made. Is it right or not?
Yes, ma'am.
So when I rotate 3 and 1, what happens is it will not come to a proper line. 3, 1 will come this side. So it again become a zigzag, means normally the same level only. Your level is not at all decreased. It is 1, 2, 3 level. When you rotate 3 and 1 also, you will get 3 levels only. Only if the levels gets decreased, your balance factor will change. That is the basic idea
Ma'am, but
actually.
the one you drew just now, that is also balanced. So we
Ah,
can just go ahead
that,
with that also.
yeah, that also. That is what I'm trying to tell. This is also now balanced only. So 1, 2. So 2 minus 1, it is 1, right? 1, 1, 2. 2 minus 1, 1. And this is 0. And this is all are zeros then. So
Ma'am,
this
but
is all.
you are doing it manually, so that is why it is coming correct. If you do like
When
uh
you code it, you will be the balance factor will be checked, and based upon the particular coding, it will be getting the alignment correctly. That is how you equate to the pointer. That's all. So this is also right. See, certain things sorting you are doing multiple sorts. One will be doing bubble sort, one is doing the other sort. So even rotation also the same thing. Right rotation only I'm doing, and it is not compulsory that you have to do only with these two nodes you have to rotate. I'm not telling you. Okay, so when you come into practice you will know it, ma. You might, I know that AVL trees, whenever I take, there will be so much of doubts, clarifications will be there, but later students will be, when they do one or two problems and when they code it, they will be knowing it clearly actually. Every time when we listen something newly, we will have a lot of doubts. That is not only you, even myself I am also telling. Even I have, when I study something new, I'll be having so many doubts. Only when we look into and implement or find something, our doubts will be a little bit clarified. Okay, that's what also I am also trying to tell you. So, both the trees are actually right. You can proceed with this or this also. So in this case, I have rotated 3 and 5. This is also right. But in the diagram which is in this particular PPT, it is 5 and 7 I have rotated. So I have got a balanced node. Okay. So now I am proceeding with this, because with this only I have solved actually. So balanced one. So now what I'm doing is, next is inserting 8. So when I insert 8, again what happens is, so you don't go and insert in the first diagram, you have to insert in the latest one which you have modified only. Okay, either this or this. So with this only I have proceeded, so I will tell you with this. Now in this diagram, where will 8 come? To the left of 10. Okay, to the left of 10, 8 is there. Now see, it is unbalanced, and you could see that this side seems to be the unbalanced one. Okay, so what you do, you know that when you view similar certain problems, when we do, we'll be knowing. So similar problem we look before also, so we know that anyway we are going to do double rotation only here, because it is not in a particular line. It is in two different zig and zag. So anyway, two rotations we need, but since we have inserted in the, so two rotations means which rotation we have to choose, LR or RL. So since I have inserted in the left side, I will choose the which rotation? This
Right.
answer? Right rotation. So RL. So right I will rotate. So I will rotate this first. So 8 goes up. Right rotation, right? 8 goes up, 10 comes down. Then again, anyway, it is unbalanced only. Now since I have processed with this, now I'll process with this both. So now left rotation, 8 and 7 will be left. So 8 will move up, 7 will come down. Now we have to check all are balanced. Now insert 20. Next is insert 20. Yes, when you insert 20, all are balanced only. So I have not done anything. Might be some mistakes, some balance, because I just drew it in the Word file, and with that only we have taken as an image and we have uploaded here. But anyway, if there are any mistakes here, I think there are no mistakes. Okay, somewhere I found, here 20 should come actually. Yeah,
Above
that's
that,
what.
10 should come.
And here also, yeah, 10. Okay, so this is what actually happens. And now when I insert 20, no problem, all are balanced. Now I'm going to insert 9. When I insert 9 also, all are balanced. Now I'm inserting 12 in the same previous diagram. Now when I insert 12, it is unbalanced. I could see -2 here and here. So what I will do is this side only. Start it from the below side itself. Don't go from the top side, don't go. Try to see where I can rotate this side. Somewhere around here. So now when I have inserted to the left side, so I will do right rotation. Right, R rotation, right. So right rotation I will do. So here what I have done is, this is in zigzag line, no, this one. So this I have right rotated it. So 12 will go up and 20 will come down when I right rotate. Now after right rotation also, you could find that there are some imbalance factors. So I will now rotate this both 10 and 12. This is the normal procedure we are following when a particular tree is in zigzag. First you will rotate this, then you will rotate this. This is the procedure we are following normally. So the same thing only. So normally most of the trees you will be getting like this only. Either it will be like this zigzag or it will be in a straight line. When it is in a skewed line, one rotation is enough. When it is something one right and one left, then there is need for double rotation. So now when you check, yeah, it is balanced. So this is what called as insertion. Okay.
Ma'am, there they are not rotating 12 and 10, they're rotating 8 and 5.
Oh, 10 and 12 is not rotated.
And how the 7 is also jumping, ma'am? I can't understand that part. Suddenly 7, if you're rotating
No,
8
no,
and
no.
5,
Wait. Yeah, okay. If you are rotating 8 and 5, not jumping, if you are rotating 8 and 5, what will happen is actually, so you can actually test for 10 and 12. If again it is not balanced, means then your possibility will go to next. You will be jumping to the next level only, 8 and 5 only. Because 10 and this, if it is not applicable, if it is not getting balanced only, you will be going for the previous value. Okay, so you can do this and see whether if you rotate
it
10
won't
and
get
12,
balanced, ma'am. It won't
it
get
won't be
balanced.
balanced because
It
we
will
are
remain
not,
like
your
that.
height is not getting reduced, I think so, right? Your height won't be reduced. So what you are doing is either, now again you check for 10 and 8 whether it will be balanced or not. If not, that is also not balanced, means here as per this diagram I'll tell you 8 and 5 is balanced. How it is going to this left is, under splay trees you have a algorithm called, when it takes play I'll tell you, but before that this is also easily understandable only. 8 and 5, when you move 8 to the top, 8's left will hold 5, so there is no place for 7, right? Actually 8's left is 7, but when you move this top node, that is your root node, and its immediate next node, child node, 8 and 5, when it is rotated and if it is having two child, 8's left will hold 5, but where will 7 go? So 7 will be replaced by, if this name is given as K2, you have to assign like K2's left will be assigned to K1's right. Understood? If this name is given as K2 and this is given as K1, what will happen is, if I'm rotating K1 and K2, you have to give that line wherever it is. Wherever it is applicable, it will work, I think so. So here, K2's left will be, because when you rotate, the other number, that is either the top node will be coming
Ma'am,
as a left. Maybe for example, here when I rotate, you see, when I rotate 20 and 12, 12 will go up and 20 will become the left child of, not, I think, right rotation, right? When it comes to right, 20 will become the right child of your 12 when you rotate right. Similarly, so when you are writing, one will be taken as K1 and one will be taken as K2 when you rotate alone. So you have to assign the pointer in such a way that when you rotate this both, when I take K1 and K2, I will assign the line as K2's left, because I know that 5 will be coming under the left of 8. So what I will do is K2's left will be equal to, I will assign the right of 5. That is the meaning. Here also you see, you forget about this 12 and 20. You see, when 12 is going up, right, 20 is coming down. So what I have to do, when I do a right rotation, I will write maybe this, if I'm writing as K1 and K2, whatever variable if I'm taking, what I will do is K1's right will hold K2. That is the meaning. Understood?
Ma'am,
When yeah.
ma'am, how are we assuming that when we rotate the node 10, then it
Hmm.
will not be balanced?
How are you
And we
as
are going that, and we are going, ma'am, we are going directly to rotate 8 and 10, right? And not rotating 10 and 12.
10 and 12, when you rotate, you won't get it, no, ma. By
Yeah, ma'am.
manually
Why?
speaking, I'm telling. By
How are,
manually, when you
ma'am?
rotate this, how will
But
you
we
see?
have to write.
See, certain trees, you will be doing it once directly, you cannot find out the answer. You have to use your intelligence here. That is what I'll tell you. When you're
Yeah,
doing, when
ma'am.
you're solving the problem, I'm telling, algorithm wise, we will see it later. When you solve the problem, you, when you rotate 10 and 12, what happens is, I told here right rotation is done, right? So here
Yes,
left
ma'am.
only.
I got,
So left rotation
ma'am, while
12,
solving
uh,
problem, I got that it will be unbalanced. But
unbalanced,
while
yeah.
writing algorithm, how will we note that?
Recursion algorithm you will be writing. You will be writing trial recursion means itself it will be going and checking each node. It will not skip any nodes. It will just find out whether when this both is rotated whether it is balanced. No means then it will go and do this. Understood? It is a recursion procedure. So
Okay,
your algorithm, when you write as a recursion, it will know that it will first check, but everything will be checked. It will check this unbalanced. Then again it will go there, it is unbalanced. Then only it will go here. Understood? So it is a recursion procedure. So now here, when you are doing it manually, you should think and little bit manage, because so that if you think and do it, you can do it in a, you can save your time. That is the thing I can tell you. When it is coming to a larger tree, the smaller tree, no problem. So larger tree, when you rotate this both, again this is going to come down, and this will, so your level will be remaining the same. So your balance factor, it will be still unbalanced. So it will go for the next 10 and 8. If that is also again unbalanced, you have to go for 8 and 5. So manually, time consumption process only. I'm not telling it is not a time consumption. When students due for university exam solve, they take little more time to solve this actually. That
and ma'am,
also I have told you.
what is the time complexity for insertion?
See here it is a binary search tree condition only. No, so you are writing as
No,
a
ma'am, full.
recursion O of log n only. Log n only. It will be, it is binary search tree itself log n only for all operations, because everything will be in the sorted way. Your left side unit, it will not go and traverse anywhere else in the right side. Since we are writing it as a recursion, your complexity will be reduced only. Okay, so when you do with 8 and 5, see here 8 and 5, it will be, now it is in a balanced mode. So that is
Ma'am, in
what.
worst case, it can be O of n also, no? If it is,
What ma?
Yes,
in
ma'am.
case it could be O of n also, no? If the tree is skewed.
Skewed, yes. The tree is skewed, it will be of n only. Both are acceptable based upon the input tree, input how the tree is actually. Okay. So this is what your, here there is a problem over here. The last you can do it and see. Yeah, you can have a practice of it. If there are more hours, I would have given you an hour and make you to practice, but running in short of time. Not, but normally every all the time, even through physical mode also, we'll be taking more classes for data structures normally. So because the subject is like that. So okay, fine, leave it out. So to find the height, what all I told now, everything is given over here. Just have a look. I'll just tell you the concept. You have a look into it. If any doubts alone, you tell me. Once again, I will explain the code, okay, in the class. So here it is giving the height. Now this is rotate with the left child, that is your ll rotation. So here I have assigned everything. You could see when you can use these lines to find out the left rotation, ll rotation. If you apply this concept, it will work correctly. Your code will balance these conditions. Your right will hold the value. So this you should work out and see this code, because I have told you this ll rotation, right? When you take this ll rotation, ll alone, first rotation, when you apply the ll rotation alone, this code will satisfy the particular condition. Similarly, this is for finding the height. Similar thing, see, these all are only rotate. When you come with double with left child, you can call the rotate with right child and rotate with left child function itself. You need not write it again. So insert, when tree is null, new you have allocation. When x is less than the element, you can have, if your height, find the balance factor. If it is equal to 2, then again find if it is less than the left element. Equal to 2 means normally your balance factors. Okay, so if it is left child, you call the rotate with left child, otherwise go with the double rotation. And if it is less than x, same reverse procedure, right child you will get. So when you are going with the lesser element, one sort of rotation will be done. When you are going with the right tree, other sort of rotation will be done. So these all just go through it once. Okay, if you find this difficult, I'll post the program in the AVL tree program, that you can go through it once. So the same thing only written here once with starting null. If it is greater, go and call insert. And if your balance factor is -2, then if your x is greater than the right side data, call the RR rotation, else RL rotation similarly. So for all RR and RL and the LR and LL, you have to write the pseudocode as I have written here. This is the main thing which carries for all. So that you go through it. I will tell you the removing also, ma. It's almost time. Okay, removing is also easy. Whenever you removing follows the exact same explanation like your binary search tree only. When it is a single leaf node, you can delete as such possible. When it is one child, immediate successor will be replaced with one child. When it is two child, can anyone tell me the condition for binary search tree? When it is two child, what I told you in the last class.
In order successor.
Yeah, you have to take the, from the left side, if you are taking, take the in order predecessor. From the right side, when you are taking, take the in order successor. Or left side, when you take the greatest element. Right side, when you take replace it with the smallest element. But each time when you remove, that is for binary search tree. For AVL, each time when you remove, you have to check for the balance factor also. This is the only difference. So construct an AVL tree in the order. So this example, already I have taught you one example. This is another one. You can go through this example. Another same example. Deletion alone, I'll tell you now. Another example, second example, okay, that you can see it. Now, when it is a leaf node, delete 11. So 11 is a leaf node, just I can delete it, no problem. Now, when it is one child, delete 12. So where is 12? So here, 12 is here. So I will replace 13. And now, actually, you have to find the balance factor also. If the tree is not balanced, you have to make it balanced. When it is with two child, what you will do is 14 you are going to delete. Either take the smallest, greatest one from the left side. So what I can replace? 13, right? I can replace with 13 only, no?
13 or 15.
Yeah, 13, or this side you can replace with 15. So anyone, delete the 14 and replace with the particular element. After that, what I think delete 14, and now what they have given is 12, 11, 13. Okay, 15. Where does this 15 come? Oh, this one.
Ma'am, that
Okay,
this
okay.
process is wrong itself, right? The
Uh,
17 will not come there only.
Yes, yeah, this don't see this. Okay, so actually what will happen is you have to first delete. So from here, take the 15 and you have to replace. No, this is, I think, after one step is left out. It's not included. A step is missing actually. This is after rotating. It is second type of. See here, what will come is actually here 15. Okay, smallest element I'll
Understood, ma'am.
replace.
Left rotation after this.
Then after that, you have to do a rotation actually, because the property is violated, because this 15 will go away and you'll be getting 15 here unbalanced. So you have to do the rotation either left or right, do the rotation and finally make it as a balanced one. That's all.
Ma'am, can you go up once? Yes,
Hmm.
ma'am. No, again back down. That is actually the perfect thing.
Actually, this is the last thing,
We'll
correct thing,
directly
I
get
think
this
so.
only, right?
This only will be getting directly.
Yes, ma'am. So
That's
why
what I am
left right
also
rotation?
seeing now sounding. But the thing is, when you are when you are when after deleting, if it is unbalanced, make it as a balanced one. That only you remind. I think this is taken from some other thing. This I have to remove it actually. I'll remove and send. Okay. So this is not the. They have put it as an image. This is not the right one. I'll change this. Two persons have combined and did the PPTs. So I think someone have misplaced this wrongly here. Okay. So this is the one, but actual procedure is delete it, replace it with the smallest or the largest one from either side, and then check the balance factor. And then if it is violate, just give a left or right rotation and make it balance. That is only uh, procedure for your AVL deletion. Okay. So this is for finding the height, and then same thing like once again given here. D with single rotate, called double rotate. If it is greater, again with left, left. Now else if both are found with two children to be deleted, replace with the find minimum. Find minimum means you have to write the minimum or find the in order traversal, and replace with the